And so here in the red we have blood cells. And then here we have osteoblasts. And so lining these blood vessels are osteoblasts. Those osteoblasts are going to make the organic matter, and they're going to deposit it out here. And so it's labeled as osteoid tissue. This is the organic matter that those osteoblasts make. And so they make more and more, and as they make it, it starts to calcify. And so now, the space between the blood vessels, where the mesenchyme was, it's starting to turn into bone, and eventually it's going to turn into bone with blood vessels, and the blood vessels are going to kind of disappear and turn into spaces. So the big blood vessels up here and here are still here, but these disappeared, but they were taking up space. And so when they went away, we now have empty spots. And so what does that look like? It looks like spongy bone, right? We had all these blood vessels, they went away, and now there's all the holes. We have more mesenchyme up here, and then there's the periosteum. So the periosteum is going to lay down more of the osteoid tissue, and that's going to turn into compact bone. And so you're going to end up essentially with a flat bone here. You're going to get compact bone that forms up here and down here. And then in here we have the spaces. There are trabeculi. And finally, eventually you end up with this, a fully formed flat bone with spongy bone in the middle and then compact bone on the top and the bottom. So this is only going to make our flat bones. This also is what's going to cause our long bones to thicken. So this makes our flat bones in their entirety, but this is what's going to make our long bones get thicker. So this is not going to stop in my forearm. This is happening as we speak. It's constantly making my arm thicker while it's being dissolved and made thinner. This is the same idea, but this is an actual slide rather than a drawing. So what we see here is we have a periosteum on the outside, and so there are two layers here. There's just a fibrous collagen layer, and then down here we have the osteogenic layer. And so what you're seeing here are cells. Those are the osteogenic cells. They're laying down osteoid tissue that's going to turn into hard bone. That's down here. So this is the new osteoid tissue that is hardened to become osseous tissue or just bone. And then we have the osteoblasts are the ones putting it down. Here we have osteocytes. Endochondral ossification is what happens to make our long bones long. This is the growth that happens at these growth plates. And so we're going to start down here, and remember, this is happening, where the way they have this is happening at the fetal level. And so we're starting basically from scratch. And so what we have here is just kind of a little thing of collagen. Okay? And so we're mostly going to skip this step. It's kind of the chicken or the egg thing. We're saying, yes, the egg exists, now let's talk about the chicken. So we're going to come over here, and so we have kind of a beginning of a bone, and a blood vessel is going to come into it. So we have a blood vessel that's going to come into our bone, and when it comes in, the middle is going to kind of hollow out. And as it hollows out, that's going to make our marrow cavity, where the bone marrow is going to end up to be. But we have up here an area where the cell is still, or not the cell, the bone is still growing. So down here, it was growing all over the place. It was just kind of a mush of cartilage and cells. Once we got kind of the critical mass, and then we started to form a bone. So it's starting to harden on the outside, but up here we have the secondary ossification center. So this is going to be where the bone is going to grow lengthwise. After a while, it starts growing, and it starts to look more and more like an actual bone. So we have the diaphysis now, and we have these osteogenic centers on each end. Separating them is going to be the epiphyseal plate. And so we have these secondary ossification centers that are putting down cartilage here, and unlike our osteoblasts, these are smart enough to put a layer down and take a step back. Put another layer down, take a step back. So as it does that, the bone in the middle, the diaphysis, is going to get longer and longer and longer. So now we are essentially a child here. And so we have a definite epiphyseal plate, whereas here we just had what's called a metaphysis. A metaphysis is the line where the growth is actually happening. So here on the epiphyseal plate, this includes 2 of these metaphyses, and then kind of just a collagen area where nothing's really happening. Over here, we hadn't grown that much, and so we just had a metaphysis where the whole thing was growing. Here, we're a child. We have an epiphyseal plate with cartilage here and a metaphysis growing here and here. And then as an adult, this is going to completely harden in. The epiphyseal line here is basically, you can't even notice it. Probably where you are, you can't even see it. I can see that it's a little bit lighter in color here, but that's now our epiphyseal line. The marrow cavity here just kept getting bigger and bigger as the bone got longer. Now we have a giant marrow cavity. We have the epiphyseal line. We formed a spongy bone on the top and the bottom, and we have a fully functional long bone. So essentially, remember what you really need to remember here is endochondral ossification is going to grow lengthwise. You have a diaphysis, and on each end you have the epiphyseal plate. The epiphyseal plate puts cartilage down and takes a step back. Puts more cartilage down, takes a step back, and over time the cartilage that it lays down hardens into compact bone. And so you'll be left with that over. Does that make sense? Whereas the intramembranous ossification kind of went inside out. You had those osteoblasts in the middle that kind of grew out. This is essentially what we just talked about.
Does this process speed up?
Go ahead. Is this your answer?
I was wondering if it speeds up at a certain point in people's lives, because some kids grow like.
Yeah. It's mostly going to be genetic. So by the time we're in our 20s, we're basically done growing, right? So this is when that epiphyseal plate is going to turn into just to have a line there. And so that gap is going to close. The secondary and primary marrow cavities are going to merge. So let me go back. And so the primary marrow cavity is going to be the one, the diaphysis. As it's growing, this is completely separate from the bone marrow here and here. So this is considered the primary. The secondary is in the epiphyses. But here, they're going to completely merge. Because that plate is now gone. The separation is gone. The two things of bone marrow can come together. Okay, so that's growth. We put that down. We put the cartilage down. When the cartilage gets down, though, it has to get hardened. I guess it's going a different way than I thought it was. So now we're still talking about growth. Okay. So remember, it has to grow in length and width. This is an X-ray. Okay. You've probably seen X-rays like this. Do you think? Oh, it says right there. I was going to ask if it was a kid or an adult. How many people can figure it out? It's a kid. How do you know? Because it says chop. But what you're really looking for is this. See how separated those are? If there was an x-ray of my hand or your hand, you would not see that. What you might see is a very, very faint line there. Okay? So this is that growth plate. By the time we get older, it goes away. Here's another one down here. Also down here. That's the one I broke. That's probably the one a lot of people broke. Basically, if you break your wrist, that's about the first thing to go. Why do you think the growth plate is the first thing to go? It's the weakest link. Yeah. It's cartilage, not hard bone. And so if you put a lot of force in this area, that's where it's going to break. Talked about so when we use the term interstitial growth, this is as opposed to, imagine the osteoblast on the outside of our cells adding more on. That's kind of outside in. Interstitial growth, it's not quite like the intramembranous. We're building from the very center out, but we are still in the bone, in those growth plates. So it's growing from the inside out. What happens on the outside is the appositional growth. So interstitial growth is the inside out. Appositional growth is happening at the surface. So this is what's really happening continuously throughout our entire life with those osteoblasts and osteoclasts. This growth, because it's on the outside, it's not at the growth plates, this is going to be intramembranous ossification. Okay? There's the two types, and endochondral is only going to occur at those growth plates, and only when you're a child. Once that's done, the only bone growth we have left going is intramembranous. So this is where the osteoblasts are going to come in. This is going to put down that bone tissue. They're going to get trapped. And they're going to, as they lay down those layers, that's where those lamella are going to come about. It's like the rings on a tree. They're going to put down a layer, and then another layer, and another layer. The bone remodeling is that process of constantly dissolving and replacing our bone. In a year, we dissolve and replace about 10% of our skeleton. So it's a slow process. I mean, you wouldn't want to do it quickly, otherwise your bone would constantly be very, very weak. But a little bit at a time, you can slowly do it. It's like if you've ever bought a house, or you will buy a house, and it's a fixer-upper, you're not going to dive in and fix the entire house in the first year. You would wear yourself out. So you do a little bit, and a little bit, and a little bit, and over time, eventually you have a new house. When you sell it, you can make a lot more money. Not only is it constantly dissolving and being remade, but there's stuff going on in that bone that affects our entire body. Right? We talked about the storage of the minerals, taking the minerals out, the controlling the pH. There's a lot that goes on here. And so if we are able to, or not able to, if we do something that disrupts the amount of calcium that's going into our bones or coming out of our bones, we can have big problems, not just with our bones, but also with the rest of our body. What's one thing you can think of, a problem that happens if we have an issue with how much calcium goes into or out of our bones? Osteoporosis, right? We're weakening of our bones. If we don't lay down as much tissue as we take up, we're going to have problems. But imagine, what if we do that? Not only are we going to have not enough calcium in our bones, we're going to have too much calcium in our blood. Because that calcium has to go somewhere. So if we're not putting it down as bone, it's floating around in our blood, then it's going to be in the extracellular matrix of our cells. When we talk about nervous tissue and what causes them to be excitable, we're going to see that calcium plays a very, very big role in that. If you have too much calcium outside of a nervous cell or a muscular cell, it's going to mess up with it's going to mess up their function. And so if you have too much calcium in your blood, your muscles and nerves won't work. If your muscles and nerves don't work, you don't work. Right? Those are two very important things. The process of putting those minerals down, putting that calcium phosphate down, is called mineralization. And it's going to take ions from the blood, and put them onto the bone. That's where those minerals are going to come from. We're dealing with a process where we take minerals in or out of the bone and put them in or out of the blood. They can go back and forth between the blood and the bone. They can't really go other places. So osteoblasts, remember, they're the ones who make the bone. So they're going to make the collagen that they're going to lay down on the old bone. Then eventually that collagen is going to get covered with the mineral. Mineral resorption is the process of taking those minerals back up. These are done by the osteoclasts with their ruffled border. And this is a more complicated process. The osteoblasts make collagen, and then eventually the collagen just kind of sucks up the minerals that are floating around, and it gets harder. In order to get these minerals back up, you have to actively destroy the bone. And so they're going to do this with proteins that are hydrogen pumps. So they're going to pump hydrogen ions outside of them into the space in that little cavity. So imagine we have the osteoclast here, the ruffled border. They're going to pump hydrogen ions into this space right next to the bone that's currently there. Hydrogen is acid. So you're essentially pumping acid into this little space on the bone. When you put hydrogen there, hydrogen has a positive charge. If hydrogen goes there, chloride goes there, because chloride has a negative charge. If you get a whole bunch of positive, it's going to attract negative. Now you have hydrogen and chloride, you just made hydrochloric acid. So the hydrochloric acid ends up in this space here, and the hydrochloric acid is going to dissolve your bone. But there's not just bone there. Remember, there's not just mineral there. The bone is made of mineral and collagen. Hydrochloric acid will break up the minerals, but then there's a protein, an enzyme called acid phosphatase, is going to break down the collagen. So the acid will come in first, get rid of all the hard stuff, all the cement, leaving behind the structure under the cement, the collagen, and now an enzyme, this protein, can come in and dissolve the collagen. So the process of taking this calcium into our bone and out of our bone is a very complicated thing. It's called calcium homeostasis. Remember, homeostasis is wanting to maintain that status quo. We want the same amount of calcium in our blood at all times. It's more important to have the right amount of calcium in our blood than it is to have the right amount of calcium in our bones. Because if we don't have the right amount of calcium in our blood, we will die. If we don't have the right amount of calcium in our bones, it's not really an issue unless we suffer trauma, right? And so we're going to prioritize calcium and phosphate in our blood over what's in our bone. The phosphate from calcium phosphate, remember, is part of a lot of different things. It's in DNA, it's in RNA. Remember ATP, that's our energy currency. It's adenosine triphosphate. So we need phosphate for this. We have phospholipids. And phosphate also helps control the pH of our blood. Calcium, we're going to see, is very, very important in our excitable tissues, our muscles, and our neurons. It's also important in blood clotting, in exocytosis, which is kind of putting things outside of our cells. We kind of use our bones as banks. If we have extra minerals, we put them into our bone. If we are short on minerals, we'll take them out. We kind of kill two birds with one stone by, when we put it in there, we also make our bones for structural purposes. We have in our body about 2.5 pounds of calcium. And almost all of that is in our bones. Just in big picture, there isn't all that much in our blood. So you can imagine you would take a lot of calcium shortage over a very long time in order for our bones to suffer. Because if you just got rid of all of the calcium in your blood, just 1% of the calcium in your bone would be needed to completely replace it. And so the vast majority of the calcium is in our bones. That's the hydroxyapatite, that was the calcium phosphate. And over time, in a year, about 18% of that calcium gets taken out and put back down. So remember, it's constantly getting taken up and then being reformed into bone. In our blood, we have about 10 milligrams per deciliter. That number is not important to me. If any of you work in a kind of a clinical setting, this may be something that you see occasionally. The calcium that's in our blood, about half of it is actual calcium ion, just a calcium charged atom flying around in our blood. And the rest is bound to proteins. The proteins in our blood like to bind different things. Small atoms, small ions, small molecules will generally grab on to a big thing like protein. And the protein will carry it around. If the protein needs to let go of it because it's needed, the protein will let go of it. That's not a big deal. If we don't have enough calcium in our blood is the key part. We don't have enough calcium in our blood, that's called hypocalcemia, like hypothermia. If we have too much, that's going to be hypercalcemia. In both cases, it's going to change the membrane potential. So remember that our membrane potential, if we have a cell, and we have our plasma membrane, our double membrane here, we're going to have positives and negatives on the outside, and we're going to have positives and negatives on the inside. The membrane potential is based on the difference in the number of positives and negatives on the inside versus the outside. So in this case, the inside is a cell, the outside is the blood. If we don't have enough calcium on the outside, these positives are going to go away. And so now we lost our balance. If we have too much calcium, we're going to have too many positives. And so we're still out of balance, we're just out of balance the other way. Hypocalcemia can be due to a number of things, but this has to do with that vitamin D talked about in our skin, right? If you don't get enough sun, you don't get enough vitamin D. Vitamin D is very important for taking up calcium. Vitamin D is going to help us absorb the calcium that we eat. There are a whole bunch of other things that can cause it. Some of them are based on glands in our body that we're going to talk about in a little bit, but also things like diarrhea can cause it. Why would diarrhea cause this problem?
Because it doesn't give you a chance to absorb.
Yes, so there's one very good reason. We need to absorb stuff out of our intestines, right? We all know all too well that with diarrhea, things don't stay in our intestines long enough, right? And so it's not going to get absorbed. How else? There's really two main reasons why. What else? Dehydration. But what goes along with dehydration? What do you think is in all of that water you're losing? Nutrients, including calcium. And so if you're having severe diarrhea, and this would have to be something like not you ate something bad, but an actual disease like cholera or something, where it's just bad diarrhea for a very, very long time. You're going to become dehydrated. You're going to lose all of these ions and nutrients with it. And so you may become hypocalcemic. Hypercalcemic is the opposite. So like we said, it's going to mess up our membrane potential. And this is really going to target our nervous system. And so this can really mess up our moods. It can mess up our brain function. It can mess up our moods and make us more emotional. It can make us sleepy. We need calcium to make our muscles go and for our brain to work. And so if we have too much of it, it kind of makes everything kind of go into hyperdrive. And it can actually make some things more active and some things less active. This is very hard to do. Why do you think hypercalcemia is difficult to do? It's in a lot of stuff, but that would seem to make it easy to do.
Because it's stored in our bones.
It's stored in our bones, and so if we have extra, we can put it in our bones. What do you think happens if we don't need more in our bones?
It's excreted.
It's excreted, or what we're going to see, we can actually stop absorbing it. And so we can stop absorbing it. We can, even if we do absorb it, we can get rid of it. And so it's kind of an accident. You'd have to break the mechanisms for getting rid of it or stopping it from coming in. Whereas here, if you don't have it, there's nothing your body can do. Your body can't make calcium, but your body can make processes to get rid of extra calcium. And so this is going to be a complicated process. It's going to be a balance of how much we eat, how much we lose through urine and feces, and the balance between blood and bone. All of these things are happening at the same time. And there are going to be 3 hormones that play a big role in this. We'll talk about each one. There's calcitriol, calcitonin, and then parathyroid hormone. We're going to talk about calcitriol first. This is an active form of vitamin D. Remember we talked about part of vitamin D synthesis happens in the skin, and then we said it goes on to the kidney in the liver. And so the first step is going to happen in our skin due to the UV radiation, and then it's going to make vitamin D3. The D3 then goes into our liver to make something called calcidiol, and then that goes to the kidney to make calcitriol. There are a lot of molecule names up here. You don't need to know those, okay? What you need to know is that the first step happens in the skin, second step is liver, third step is kidney. If you've had any sort of organic chemistry, which I realize a lot of you haven't, what's happening is up here, we're going to add a hydroxyl group, and we're going to add an OH. And when we name organic molecules, an OH is signified by an OL, like alcohol, okay? Methanol, ethanol, those all have an OH on them. Here in the liver, we add a second hydroxyl group to get a diol, di for 2, all for alcohol. And then in the kidney, we add a third to get triol. Yeah, go ahead.
Are they getting the hydroxyl group from bringing out water or something?
Mostly water, yeah. So water in our body is constantly getting broken down and used and also made at the same time. So calcitriol is going to increase blood calcium. So remember, 2 things have to happen at the same time. If you're increasing blood calcium, it's also going to means it's going to take it from the skeleton. So calcitriol is going to take calcium from your bone, put it into your blood. It's also at the same time going to increase how much you absorb. And then it's weakly, just a little bit, it's going to have some effect in the kidney to decrease how much your kidney is going to get rid of. We're not going to talk about the kidney in our semester, that's next semester, but the kidney is really unique because instead of deciding what it wants to get rid of, it actually takes pretty much everything out of your blood and decides what to put back in. And So what this is going to do is it's going to tell the kidney, need to save calcium, put more of the calcium back into the blood. So it's kind of a catch-22, because calcitriol promotes taking calcium from the bone, putting it into your blood. But it has a big role in absorption of calcium at the same time. And so if you get rid of it, you're not going to absorb calcium from what you eat. And so you're going to become hypocalcemic, and you're not going to have any calcium to put down on your bone. If you don't have enough of this calcitriol, your bones are going to become soft. If in kids, this is called rickets. In adults, it's called osteomalacia. Okay? From what I've seen, a lot of people still call it rickets. But officially, it has a different term in adults. And so we have some different things going on. Okay? So over here, we have calcium coming in. So this is dietary requirement. It says about a gram a day. So you're eating the calcium. It's coming in. It's getting absorbed here. But you're also losing some. It says we lose 350 milligrams, which is about 0.35 grams a day. And so we're taking in 1,000 milligrams. We're losing 350 milligrams a day in feces. We eat it, it's in our digestive tract, it's going to get absorbed. And so here we have a matter, it's showing that calcium is getting absorbed from our digestive tract into our blood. When you see an arrow like this is based off kind of our yields arrow in chemistry. So this is saying it's taking something from here and turning it into that. And when we put calcitriol under or on that arrow, it's saying calcitriol is making this happen. So this is saying that calcitriol is making the calcium that we ate in our digestive tract come over into our blood. So now once it's over here, it's also going to take some of the calcium as it goes through our kidneys, is going to go out in the urine, but the calcitriol is also going to help bring some of that back. So it's going to help us absorb the calcium. It's going to help us prevent losing it in our urine. So down here it says we lose about 650 milligrams per day in our urine. 650 plus 350 is 1,000, right? And so in a perfect world, we would eat and lose the same amount of calcium every day. In a child, do you think that's the case? No. Why not? You're right. You're perfectly. You're very right. I was actually looking in a different direction.
Because they're growing.
They're growing, and so hopefully they are eating right, and they're taking in enough to overwhelm how much they're losing. So they're going to lose less, and hopefully their diet has a lot of it in it, right? Kids drink a lot of milk, a lot of calcium in milk. And yes, you've probably heard of milk. I'm from north. It's not milk. Milk is just foreign to me. Okay, it's milk with an E. But I spell it with an I. I spell it with an I. I'm not a heathen or something. Okay. So calcitriol is going to be over here, and then there's going to be calcitonin here. Calcitriol is another effect. We said it can take calcium from our bone, put it into our blood. So calcitriol is in 3 places here. Absorption, preventing kidney loss, and also taking it from our bone. Here is calcitonin and parathyroid hormone that we haven't talked about, but they're coming up on the next slide. So this is calcitonin. This is going to come from part of our thyroid. So our thyroid has several functions, a few different types of cells. One of them is called C cells. These are clear cells, and these are going to secrete calcitonin. The thyroid is going to be able to determine that the calcium in our blood is too high. If the calcium in our blood is too high, the thyroid is going to secrete calcitonin, and this is going to lower the blood calcium. There's two ways it can do it. Number one, it's going to inhibit the osteoclasts. The osteoclasts are the ones that are dissolving our bones. If you can inhibit them, you leave more calcium in your bone and you keep it out of your blood. It's also going to turn on the osteoblasts. So you're going to turn on the cells that take calcium from the blood, put it into the bone, and you turn off the cells that are taking it from the bone and putting it into the blood. This is really important in children, not as strong in adults, because children need to grow. If you have a constant balance between the putting down and taking up, the bones will never grow. You need to inhibit those cells that are taking the bone up and stimulate the ones that are putting bone down. And so this is very active in children. It's not nearly as active in adults, but if we have too much calcium in our blood, it'll kick on. It's sitting there waiting for its time. The third one is parathyroid hormone. Okay, this also is going to come from your thyroid, but it's not just the thyroid. So next to your thyroid, we're not going to talk too much about the endocrine system, are the parathyroid glands. They're right next door. Okay, it looks like kind of one organ, but they're not. So this is a separate gland, and this kicks in when calcium gets too low. So the thyroid turns on when calcium is too high. If calcium is too low, your parathyroid is going to turn on. And this works in 4 different ways. Number one, it's going to make osteoblasts put out a protein called rankle. And rankle is not a name you need to know, okay? But when it does that, it's going to increase the amount of osteoclasts. So rankle is going to promote the formation of osteoclasts. And osteoclasts, remember, can serve multiple purposes. One of them is bone resorption. So essentially what this is going to do is going to turn our osteoblasts into osteoclasts. We're going to take cells who only have one purpose, to make bone, and turn them into cells that can do both. So the net effect is that we end up making less bone. We end up taking more bone up into our blood. It's going to have a similar effect in the kidneys like the calcitriol. It's going to prevent the calcium from leaving through our kidneys in our urine. It's going to make more calcitriol. And so that last step of calcitriol synthesis was in our kidneys. So it's going to help that process. So we'll make more calcitriol, which will help us do all of those things calcitriol did. And finally, it's going to inhibit collagen synthesis. And we saw that collagen synthesis was the basis of making bones. We put collagen down, and then it hardens. If you don't put collagen down, it can't harden, and so your bone can't get bigger. So parathyroid hormone is kind of a complicated thing, right? But essentially, what it's going to do is it is going to prevent loss of calcium. It's going to get more calcium in our blood to bring our calcium levels back up. So here's the situation. We're going to start here. So we have excess calcium. What gland is going to turn on? Thyroid. Just plain thyroid. Thyroid will kick in. It's going to secrete calcitonin. Calcitonin is going to do 2 things. It's going to turn off the osteoclasts. It's going to stop bone dissolving. It's going to increase osteoblast. It's going to create more bones. Both of those things are going to take calcium out of the bloodstream until our blood comes back down to normal, and then the whole system will shut back off. Once it's back to normal, this calcitonin will stop being made, the thyroid will turn off, at least this function of the thyroid, and then it'll just wait until things get out of whack again. Here, we have a blood calcium deficiency. So the parathyroid is going to turn on. It's going to make parathyroid hormone, and it's going to do those 4 things that we talked about. So we talked about the 4 roles of parathyroid hormone. They all have their effects, but they all help the blood calcium levels go back up. Similar things happen with the phosphate. Calcium is the biggie. Calcium is more important than phosphate, but the phosphate is also important, and we also have to manage it because, remember, most of our bone is calcium phosphate. So if we dissolve calcium phosphate to get calcium, we're also going to get phosphate. The calcium and the phosphate, for the most part, are linked together. We can't deposit one without depositing the other. We can't reabsorb one of them without reabsorbing the other. We don't have nearly as much phosphorus as we have calcium. We say, like they said, 2.5 pounds of calcium. We have a lot less than that in phosphorus. 500 to 800 grams is probably about a pound. And almost all of that is in the bones, but it's not quite as large a percentage as the calcium. We have another normal range, but again, that's not an important number for our class. This is going to exist in 2 forms. It's going to be monohydrogen and dihydrogen phosphate. And because the phosphate isn't as important in our bodies, the normal physiology of phosphate isn't as important as calcium. Because phosphate doesn't have the ability to cause our muscles and our neurons to wig out, it's not as important to control its levels. But calcitriol also has an effect on phosphate. So calcitriol is going to raise phosphate levels, and it's going to do that by causing our intestines to absorb more of it. So usually a lot of it's just going to pass through, we're not going to absorb it, but if we have calcitriol being made, it's going to help us absorb that phosphate. Parathyroid is going to lower blood phosphate, and that's because it's going to cause the kidney to secrete it. And so if we go back, parathyroid, what was its role here in the urine? It causes the kidney to get rid, or keep calcium, but it's going to cause it to get rid of phosphorus. And so it actually has opposite effects on the calcium and phosphorus. How many slides do we have left? Is there 4? Let us take another break. We have plenty of time. Let's take a 9-minute break. We'll come back at 8 o'clock. you're losing that much blood, you're probably having to get blood transfusions, so they can probably just spike it into the blood transfusion. That would be my guess. Because having the blood is a lot more important than having the calcium. Calcium is an issue long term.
But it seemed like, I'm pretty sure, no, it was having the she had calcium phosphate back.
I don't know enough to tell you that.
I feel like this
It
is
could
gonna
be
be
that,
another
but it
commission
could also be
for me.
wanting to have calcium in terms of muscle contraction. What do you guys? Or is it? Yeah, so there's something specific.
You said it was, what it reminded me
Great, but what was that thing?
of the centrals, the replicating, and all that.
So if you had sort of general biology, you come in the cell cycle, you are.
I'm looking at you sell it before I came here. I was like, ain't no way.
Probably, so one of the things that controls the cell cycle are some proteins called CDKs. That probably but there's some proteins that control the CDKs, control the cell cycle. And you can imagine cancer wants to grow really fast, right? So it wants to speed up the cell cycle. And so a lot of times cell cycle proteins upregulated with CDKs. So what I found was that as a byproduct of that, that same CDK that speeds up the cell cycle causes the cells to make too many carbohydrates.
Just the centrosome or everything?
Well, it has a lot. It has a lot of effects. And then basically, that sort of that can look at we look at the specific, very very specific complex proteins, trying to figure out what they do. Because in normal cells, this complex doesn't form, but in some breast cancer, you get way too much of one of the proteins, and start grabbing on to the other ones to make this complex. So my project was looking at how that complex causes centrosome duplication. And interestingly, not only cause that, but cells have normal processes will recognize I don't have the correct number of chromosomes, it stops dividing. And so I had to find this other mechanism where it was destroying them for protection factor also.
It acts as like
No,
$3 on the card and then cash.
and there's a
However much amount. But if you're using card, they'll
most
only
of
take
the work
$3.
that you just look at cells, you're normally looking at tags,
So I would just do cash.
which is
Yeah,
not.
it's a lot easier that way.
then you can't.
Thank you, sir.
Regular.
No, it's very good. So, one thing we can do.
You have a manager electron sheet.
No, what you can do is you can make different proteins in the cell with different colors. So you look at the cell in the dark, and you can see where the things are. Here you can see red are centrosomes.
Yeah.
The blue is egg. And then in this picture, exactly.
So gonna go.
Down here, this is the green
Oh, you're
state.
going.
This is actually just the centromere, which was the chromosome.
I do feel so true.
So right here, you can really see this is normal.
They stopped the blood pressure stuff.
Sometimes cell divide into three cells, in which case none of them have really chromosomes as opposed to here. But sometimes it will divide into two. And so what you see here is what this cell did in the long term.
Still the cytokines.
It's still doing the cytokines, it's dividing into two. Most of the DNA is here and here. And you have two chromosomes that are dividing into one. You see? And so eventually cytokinesis is going to happen. If it happens here, you'll be okay. If it happens here or here, one cell's going to lose a chromosome and gain a chromosome.
When it's happened in the reproductive cells.
It could be much less quick because they have
You could have twins on Down syndrome or not.
most likely, yeah.
I think it would die.
I mean, sooner than so my guess is trying to so possibly one would be born with Down syndrome, the other one would be born with probably. So here, this is a monopolar circle, so there's only one center. Of course, you actually see are the two central holes making one centrosome. So there's only one spindle. And so instead of looking like this with two down three, you get one spindle and you kind of go with the pancake.
What happens to that thing?
What happens is it can't undergo cytokinesis. It kind of just fails and it continues. Now it can double the DNA it's supposed to. Because it doubled the DNA so it can divide two. So it didn't pop. Now it has twice as much.
So does it eventually die or does it keep going and going?
That's not the other mechanism. So a normal cell can go twice as much DNA and die.
Yeah.
And so the CDK had to not only cause this, but prevent cells that look like this.
Hopefully you got it figured out.
Published, you can look it up online. It's there.
I won't know all the windows. I need to make sure I didn't make a color those things.
Yeah, it is basically you get different antibodies for all the different proteins, and you just attach each antibody to a different color. So an antibody specific for centrosome is red, and an antibody specific for spindle is green. And you just put as many together as you need.
Those are all bright.
Yeah. So you need to do it, you need to be good at it to get bright, and very dark background. Okay, so we talked about bone growth, both in sort of the big sense, in the cellular sense, and then actually kind of the molecular sense. Now we're going to come back and talk something similar about with fractures in bone repair. And so this is going to be an actual big fracture, not little tiny microfractures that happen all the time, but an actual big fracture. And so this is going to be a stress fracture. A stress fracture is going to be a big stress on a bone that causes it to break. Okay, the picture we're going to see, the diagram we're going to see, is a bone that is literally broken. A pathological fracture is something that's going to break due to a stress that normally wouldn't cause a bone to break because your bone is weakened. So the bone was weakened and then it broke when you applied a normal stress to it. It's imagine someone who's very old who has osteoporosis. A lot of times when they fall, they break a lot of bones in their body that you or I would not break, right? It's really bad up north in the snow. If you live in the snow, at least a few times a year, you're going to land on your butt because it's ice. But for most people, you get up, you curse a little bit, you get in your car, and you drive away. If you're older, though, falling can literally kill you because you can break so many bones in your body that it releases all these bad chemicals in your blood. That can kill you. It causes so much pain and stress that can kill you. This is very, very bad news. But a pathological fracture is breakage of a bone due to a stress that shouldn't happen. But if I slam my finger in a car door, I don't care how much milk you drink, you're going to break. That's a stress fracture, right? You can also classify fractures based on what they look like. We're not going to get too much into it, but we can classify fractures based on what direction fracture goes. Does it go perpendicular to the bone or parallel to it? Whether the bone is sticking out of the skin or whether it's still in the skin. How many pieces we've broken it into? Did we break it in half, or did we completely shatter it and it's in 10 million little pieces? That's not a word you have to know. So this is the one we're going to look at. So we have a long bone, and we've broken it essentially in half. There are some little tiny fragments here, but for the most part, we just broke it in half. When you do that, you're going to have the formation of what's called a hematoma. That is essentially a bruise. It's a bruise / blood clot. And that's going to find that fracture, and it's going to fill it in. Because you don't want an open space here. Because there's stuff outside the bone that you don't want in, and there's stuff inside the bone that you don't want getting out. And so you're going to form this hematoma and just cover the wound. Over time, the hematoma is going to sit there, but more permanent things are going to start to show up. We're going to form what's called a soft callus. We're going to start putting cartilage down in here. It's going to turn that blood clot into something a little bit firmer. And the blood vessels, I mean, we had lots of blood vessels here, but they're going to get, the ones that were there are going to get destroyed. But because we need to grow a lot here, we're going to need a lot of blood. And so we're going to get blood vessels growing in here to replace the ones we lost, but also additional ones to speed up recovery. Our soft callus is going to turn into a hard callus, so it's going to start to calcify. In addition to calcifying, the spongy bone is going to start to grow back. And then finally, over here, the spongy bone has completely finished here, and the entire hematoma and soft callus is turned into hard, compact bone. What you see here is a knob, right? You see the knob at the fracture looking sort of like the hematoma. Do you think that's like that permanently? Nope. Why would it not be?
Osteoclast.
Right. That constant absorption and breakdown, right? Yes.
When I broke my collarbone, I now have more bone
Do you?
there than there was when I broke it initially.
My guess would be I mean, it's going to be a very long process. I mean, we said only 10% of our bone gets taken up in every year. So my guess is as you get older, it's going to get smaller and smaller and smaller. Whether it'll completely go away by the time you go away, who knows, right? Hopefully it does. That means you went away a long time from now, right? But this bulge is not going to stay there. It's not. The goal is to get rid of it, to get it back to looking exactly like it looked like before. Okay, so that is kind of the physiology of the bone. So we're done with physiology. Now we're going to have to talk just a little bit about anatomy. In the lecture, we don't have to memorize a whole bunch of bones. That's coming in the lab, but not in lecture. We have to talk just about a few, but we're not going to say, here's